Testing, testing. Okay, let's see how we go. All right, so this is going to be the last video I'm going to do in this holiday series. So we're going to have a look at circular motion in a vertical plane. Now, there's not a lot of new information, but there's a lot of old information that we need to go over. So I've just written a little summary sheet here. Okay, things to consider. All right, so we're talking vertical, so with vertical motion, we've got to consider gravitational potential energy. So when you change that, you're changing the height. If you're going higher, you need something to, well, you'll be gaining gravitational potential energy, and that energy has to come from somewhere. So also remember, I might even add, law of conservation of energy. Okay. So that's, the total energy of the system cannot be created nor destroyed. So we're going to be changing between the two of these, gravitational potential energy and kinetic energy, in a lot of these problems when we need to. All right, so if you lose height, you'll gain kinetic energy, and if you gain height, probably means you've slowed down, you've lost kinetic energy. Okay, so the forces involved, okay. Well, since we've got vertical motion, gravity, we're going to use the simple weight formula. Weight is mg. All right, centrifugal force. So this is we got circular motion involved here, so we need to consider that. Normal force. That's what's going to provide centrifugal force, but it's a bit more complicated because when you've got gravity acting on a surface, so if it's flat. Then the normal force will counter gravity. But then if you've got something that's a curved surface, you have gravity and centrifugal force acting perhaps downwards, or in one case might be upwards. The normal force will vary depending on the circumstance, so we'll come to that later on. There's also this concept that we learned about in gravity, apparent weight. So remember that that's the kind of the weight that is experienced, and it's basically, it's in most cases you can consider it the same magnitude as the normal force, but down instead of up. But we'll come to that in the problem solving. And in general, ignore frictional forces, ignore energy loss to other such things as heat and friction and whatnot. Okay, so we don't have a lot of resources to work off, so I'm just going to pretty much work off the book. So a main application of this is, for example, roller coasters, where you have changes in speed. The direction of force, because we have a lot of curved surfaces, the direction of force makes it quite complicated. So that's generally when you would want to use, when you're talking about picking up speed, you want to be using energy, because you don't have to worry about vectors in that sense. You can just say, okay, well, I started at a certain height, I ended at a different height, and if that's down, that converts to kinetic energy, and if it's up, it's kinetic energy converted to potential energy. But we also are considering the motion in circles and where those forces might be at particular locations. All right, so let's have a look at some of the concepts we got here. All right, so moving in vertical circles. All right, the speed of skateboard practice in half pi increase the way down the gravitational potential energy, converting kinetic energy. This means the skater experiences linear acceleration as well as centrifugal acceleration. All right, so you remember centrifugal acceleration. We're not bothering. We're not really considering that to be a change in magnitude, but a change in direction. So there's linear acceleration, in fact, that are picking up speed if they're going down, and if they're going up, that will be reversed. They'll be losing velocity. I'm sorry, losing speed, and velocity is changing. In the case of linear acceleration being the magnitude, and direction in terms of centrifugal acceleration. All right, so you can read that in more detail. I'm just going to go through the cliff notes for these. All right, so we've got some images alongside here. Maybe I might even I'm going to stream that down for a bit until we do some problem solving. Okay. Okay, there we go. That will do. All right. So I might just go back to that last one because there was the image associated with that. No, there wasn't. I thought there was. Oh, there it is. Yeah, it's on the left hand side. It's on the left hand margin. Okay. So the idea, yeah, essentially, unlike the horizontal one where you can say horizontal circles, well, there's no change in speed. But okay, there's a change in speed and there's a change in direction, but we can separate these concepts. So in terms of the energy potential becoming kinetic, there's energy transfers that can that height mgh converts into kinetic energy. So there's a linear speed picking up. So they've drawn this vector arrow in that direction. That's the net acceleration. All right. It's easy to kind of consider this at the top. At the bottom of the ramp, though. So here, there's no more kinetic energy to be gained because the lower it's going to go. So the acceleration is entirely up towards the center of the circle. So now we're just changing direction. And if they travel back up, they'll be slowing down. Okay, so let's move on. All right, so I'm just going to summarize some key points. Welcome to read this further, and I would recommend that. Let's get rid of that. Get that. Don't need that. Okay, so let's adjust the direction of this. There we go. There we go. Okay, so so if you're moving a straight line in this scenario, so uniform horizontal motion, then the force of weight in the is going to act downwards, and that's your mass times gravitational acceleration. So there's 50 kilos, there's 490 newtons, and then you need 490 newtons of normal force so that is not slipping through this. Now, when you're moving through a curved section like this in a vertical dip, all right, consider the forces that are in play here. So again, you've still got the weight force acting down on this section. So imagine you're here at the bottom again, and the normal force, well, what's that going to be? Well, you've got both the weight force and you've also got, this wants to keep traveling in a straight line. So you have the normal force is also what contributes to the centrifugal acceleration. So is the normal force that's pushing this up to turn, as well as countering the weight force. So it's actually doing both. So let's have a look at what they've done here so far. All right. So they've gone and worked out the centrifugal. So they've got the centrifugal acceleration, and they've gone and multiplied that by mass. So this is your centrifugal force. So this is the force here. That one. That's that there. That's the force required to turn this around. So what they do now is the total normal force is the force that counters the weight plus a centrifugal force. So at the bottom of the pike, you combine both. You have a scalar addition of the two forces, ends up with a total force of 1,790 newtons up. So that's a lot more force than just the weight force otherwise. So, and they also describe that this is the reason why in a ride you feel the seat push you up against you much strongly at this point. And they make reference here again to the parent weight. So this is where the parent weight is at its highest. All right. So what about the other scenario when you're going over a hump? Well, the argument is in reverse. So in this case, you're going to be turning around this way. So remember, if you turn around the circle, the direction of the centrifugal force is in towards the center of the circle. So the centrifugal force is down, and that's so you actually to get that. What they've gone and done. So let's have a look at that. All right, so they've done a similar calculation. Centrifugal acceleration times by the mass. Okay, so then the force is downwards. All right, as in the dip, the weight force and the normal force are not in balance. They will give a net force of 80 newtons down. The weight force Fg must therefore be 80 newtons greater than the normal force. All right. Now you notice because the normal force was in the opposite direction, they've used a negative vector. So in this case, the normal force is the opposite of the weight force. So that's the weight force is 490 newtons down. The centrifugal acceleration is 80 newtons down. The normal force opposing the weight force will be 490 newtons up. Then you got minus 80 newtons down. So and you end up with a total force of normal force of 410 newtons up. So this would be a reduced apparent weight. So you feel lighter when you're going up this section than you would otherwise, because you don't experience the same force upwards. You experience a diminished force up from your seat when you're sitting on this section of the ramp. All right, and I think they probably mentioned that in the next section. Okay. Yeah, and they summarize this here. So they're comparing the two. Three situations. Oh, okay, what was the other situation? Sorry, I'm missing one. Oh yeah, horizontal. Okay, that's a trivial case, but it's good to summarize that anyway. All right. So normal force when traveling horizontally is that. So at the bottom of the dip, you've got a significantly larger normal force pushing upwards. At the top of the hump, you have a diminished normal force. And it's not diminished by much, but also remember that's the slowest part of the ride. So you don't need as much centrifugal acceleration because you'd have a lower velocity. I might just make mention of that. I'll just go back and say at the bottom of the dip, you have 8 meters per second. At the top of there, you're moving at 2 meters per second. So I'll just make a point of that, which makes sense. Okay. The weight of a person is not changed throughout the duration of the ride. The normal force acting on them varies. The normal force is equal to the person's apparent weight and makes them feel heavier and lighter as they travel through the dips and the humps respectively. So this is the idea, having a bit of fun, you're riding on a rickety ride that makes you feel experience forces in different ways. Okay. So it's not meant to be necessarily smooth. Okay, roller coaster cart going through dips and humps is always moving above the roller coaster track. So normal reaction forces are acting upwards. It's also possible for a cart to travel on the underside of the track and it's going upside down through the loop. And we'll go through an example of that. Okay. All right. So I'm just going to summarize a couple of things about this sort of example. You can read these for yourself, and I'll try one from the book in a minute. Okay. So you've got a toy car here, mass associated. It is 1 meter above the ground. Notice that at point X is 1 meter above the ground. At Y, it will be 1 meter lower than that. And at Z, if you go and take account of this, that would be 0.4 meters, or 40 centimeters above Y, which would be, that's actually a drop from the top of 60 centimeters. Okay. So you could use the energy calculation to do that. So go back to using your MGH in order to work out what the speeds are. There's no doubt that's something you have to do. It's released, so it has a release from rest to make it clear. So at that particular point, it is traveling at 0 meters per second, and conversion to kinetic energy is what makes it speed up. And yeah, there you go. Use energy arguments to calculate speed. I'll go through an example of this myself in a minute, but you can read that one yourself. Okay. And continuing with the problem, now we need to consider the normal reaction force at point Y. So this is very similar to the example that went through before. And actually in this case, they've gone straight to work out the net force, which is the centrifugal force. So net force centrifugal Because basically, you know, the gravity and the weight force are cancelling out because it's not falling through the track, nor is it flying upwards. It is turning as it goes around. All right, so the net force is that. At the bottom, anyway, higher up it has translational acceleration and a linear acceleration, as they call it before, and further up in linear acceleration backwards because it's slowing down. Okay, and yeah, this is like the example before, but we'll go through some problem solving this. And at point Z, just remind you, point Z, you can either use the point previously worked out here at Y. I would actually go and use the, I'll go back to X and Z and just say, okay, well, you dropped by 60 centimeters. I'm curious, how do they do it? Okay. Yeah, at point, okay, work at the, oh no, sorry, normal force, what am I talking about? All right, this is interesting, worth watching. All right, so you're on the other side, as we can see here. You've got weight acting downwards, and you've got centrifugal acceleration, which is also acting downwards. So you can consider those things. So net force is a combination of the normal force and weight. Okay, so you can work out the normal force from there. So the net is your acceleration. You got to calculate that, mv squared on r, and that's downwards, so we use a negative. And weight is downwards, so we use negative. It's useful when you've got up and down vectors. The convention is to use down as negative and up as positive, but if you're consistent within your own question, it won't matter. So if you did down as positive and you end up with a negative answer, that would imply that it was in the opposite direction, therefore being upwards. Okay. So rearranging this, they can solve for that, and they end up with the normal force is actually down, which makes sense because it's underneath the underneath here. So yeah, the track has to push, the cart's actually pushing up because it wants to travel in a straight line. If you could switch off gravity and this path would go away, it would travel in a straight line at this point. It would travel to the left. But gravity will make it move in a parabol, but this track wants to make it move in a circle. So the cart is actually pressing up in its inertia to try to move straight. So that's why there's a normal force acting down. Yeah. So, I mean, if this had no velocity, it will drop. So that's, yeah, the idea that is inertia that is providing a force on upwards onto the track, and the track's pushing down, and that's what's causing the, well, a part of the centrifugal acceleration. Gravity is also at this point providing part of it as well. So gravity is providing 1.4 newtons of that 8.82. All right, so let's have a look at some problem-solving questions. Yep, traveling up without falling out. You can read that yourself. That's a bit interesting. Okay, let's summarize a few points. Yeah, going through that. If normal force is greater than the gravitational force, the passenger will feel heavier. If the normal force is less than the gravitational force, the passenger will feel lighter. In vertical motion, gravitational force always acts vertically downwards, regardless of position in the circle. Net force always acts towards the center of the circle. Well, that's in particular the net force when you're at the bottom or the top. So then you're not worrying about you're at peak velocity, maximum or minimum, thereby not worrying about linear acceleration. To be clear, all right. Normal force and the gravitational force must be added together as vectors to force diagram to give the resultant net force. And notice these are always one-dimensional vector diagrams. So you just have to consider up and down. Thereby, yeah, if you have both, consider up being positive, down being negative. All right. The point of the object lifts off from its circular path. The normal force is 0. The object will be moving for centrifugal acceleration is equal to that of gravity. All right, problems involving, yeah, and we've got energy arguments there that I've gone through. Okay, so let's try some problem solving ourselves. So let's get a bit of space. All right, and I might make this a little bit smaller. All right, so I'm going to jump into some probably some more challenging ones. Well, maybe I'll verbally state a few ones. Let's start with. Describe the magnitude acceleration of a yo-yo along its path. I don't want to go into the translational spinning of it. Yeah, it's actually this. Oh, it said there we go. A yo-yo is spun at constant speed in vertical circles. So we're not thinking. Okay, I made that clear. Well, the magnitude acceleration, the net acceleration will be, it's a constant speed, so it's in a vertical circle. So the net acceleration will be pointing towards the center of the circle and a constant. Okay, at which point of the circular path would be a greatest amount of tension in the string? That would be at the bottom. So if I was to kind of draw the yo-yo in the case, it's okay, the yo-yo is here. All right, at the bottom, you would have a weight force, and you would have a net force, or net, yeah, well, let's write forces, because then you can add forces and vectors. Just be careful with that, and acceleration doesn't quite work. Okay, and you got force of gravity. And it's the, okay, so the tension force, so net force is this, and remember that in this case, net force is what's providing centrifugal acceleration, and then that's the combination of the weight force plus the normal force or tension force in this case, as that's what's providing, oh sorry, yeah, it's not a normal force, it's tension force. So in this case, the tension force would have to be larger because it has to give that net force plus counter the weight force in the opposite direction. Whereas at the top of its path, then you'd have weight forces down, net forces down, and you would have a smaller amount of tension force because there's these two add up to make the net force. So that's that one. Okay. At what point is the string most likely to break? Well, where the tension is greatest, which is at the lowest point. Okay. All right. Maybe I'll take, just for the sake of it, let's take question 3. All right. All right, question 3. A car of mass 800 kilograms encounters a speed hump radius 10 meters. The car drives with a constant speed of 44 kilometers per hour. Let's fix that up immediately and let's take all the details we have. Okay, let me get my trusty calculator out. Okay, calculator. All right. So here we go. All right, so 144. 40, it's 14.4 divided by 3.6. Okay, that is now 4. Well, that is now nice. I give us a nice round number. That's pretty nice of them and give all the details as well. All right, so we've got mass 800 kilograms. Speed is 4 meters per second. And speed hump has a radius. Radius of 10 meters. All right. All right. So it's like a big hump, and your car has to go over that. So it's going over that, traveling over. Okay, and that's 10 meters. All right. So at the top of the hump, so name all the forces. Well, let's have a look. We've got, let's rewrite them down because we can state them. You've got weight force. Well, actually, why not? Let's just listen this way. Weight force, gravity. You've got normal force, and you've got centrifugal force, which is basically going to be the net force. All right. So calculate resultant force acting on this car when it's at the top of the hump. All right. Okay, so let's go and do that. All right. F net equals Fg plus Fn. Okay, so we can work these out separately, but for the sake of it, because you've seen a few examples, let's just go and do it. Mv squared on R, so there's net force is centrifugal because that's what's happening. Okay, mg plus Fn. You could work this out in one formula essentially just by moving that over, but for the sake of it. Okay. So there we go. Let's just do this. 800 times 4 squared over 10 equals 800 times 9.8 plus Fn. Okay. So trusty calculator. Let's just work these out in bits. Oops, too many. Divided by 10. There we go. 7,840 plus Fn. All right. 800 times 4 times 4 divided by 10. I should really have my scientific at least, but I don't have it with me right now. Okay. All right. And if you just go and isolate for Fn, you need to subtract these two. Now, did I get the directions for those? Okay, centrifugal will be down, weight will be down. Now, let's see what I've done here. I just went and plugged these in. I was being a bit reckless. So I'm going to end up with a negative answer. I need to interpret that correctly because both of these were down, so I haven't moved anything yet. But because I didn't plan for this, I'm going to end up with a negative vector answer, and I have to interpret that as the opposite direction. Of course, the force normal is up in this instance because we're on top of the ramp, on top of the surface. So subtracting that across. So I'm actually going to do that here. Subtract 7,840. Okay. Negative 6,560. So I'm going to just then write that as positive 6,560 newtons, and the negative is the context of the direction, which is up. Okay, there you go. So there's the final answer. All right. So rest of part 3. After traveling over the hump, the driver remarked to the passengers she felt lighter as the car moved over the hump. Is this possible? Yes, that is apparent weight. So because there's a reduction in the normal force. Normal force would otherwise be this, which is just the weight force. So yeah, there's a reduction in the weight force, so the apparent weight is lower than the weight force. Therefore, you experience less force upwards through the chair. Okay, so that's part C. I just explained it. All right, part D. What is the maximum speed in kilometers per hour that the car could have a top speed of a hump and still have its wheels in contact with the road? Well, okay. Well, basically when the normal force equals 0. So let's have a look at that. Okay, so let's just go back to this equation. All right, we'll have mv. Okay, mv squared on r equals 740 plus Fn. So that's kind of the, okay. Well, now we're solving for v. Now, basically, when the normal force can't provide that anymore, so when the normal force is basically negative 7,000. So basically, when this goes to 0, is that right? No, sorry, it's when Fn equals 0. I just realized that's not going to work. because then I'll just get a velocity of 0. So let's try that again. Okay. Try that again. So 4 plus, it's when Fn, normal force becomes 0, because right now it's reduced. So you can say travel it faster, and if you travel it faster, you would have subtracted a larger number, because that number would have been larger. You subtracted a larger number than this one. Okay, so mv squared on r. Okay, so Fn's gone to 0. Let's just put in the rest of the known variables. Okay, 800 v squared on 10 equals 7,840. That's the centrifugal force. No, that's the weight force. But then normal force is gone to 0. All right, so then we can just cancel all two of those. Okay, so just basically divide that by 80, and you've got v squared. V squared equals. Let's move my camera. Okay, focus here. Okay, so v squared equals 7,840 divided by 80. Okay, 98. All right, and square root of 98. I actually don't know how to do a square root on this. That's right, that's what the internet's for. Okay, let's use our calculator here. Where's come prepared? Bring your calculator. All right, so 98, let's take the square root of that. Oopsies. You want to do it the other way around. Okay, fair enough. All right, so 9.899. Okay, run that to 9.9. Okay, well, is that what they wanted? 9.9 meters per second? No, they wanted kilometers per hour. So let's do that. So 9.900, so effectively times by 3.6. Okay, so and that's approximately 35.6 kilometers per hour. There you go. Okay, so that's what they wanted. Okay, yes, and then we just answered that, didn't we? Okay, let's have a look. So I want to do let's do one that includes energy. I could do this one. This one's interesting. Let's maybe look for another one. All right. Yeah, let's just do. I'm going to do question. Oh yeah, let's do question 10. All right. Next page. Next page. Okay. Gonna switch page up. Okay. All right. New page. New page. All right. So question 10. This one here. Let's just set that up. All right. So a ball bearing of mass of 25 grams. So let's go and fix some stuff up. Mass equals. Divide that by 1,000. Okay. 25. Yeah, I think that's right. Okay. So I moved it up 1, 2, 3. Yes, that'll be correct. You always check with your calculator. I'm not going to. All right. Is rolled along a smooth track shaped of loop-de-loop. The ball bearing is given a launch speed A so that it maintains contact with the track as it passes through point C, ignoring air resistance. So it just maintains. So basically, it's just given a nudge. For all intents and purposes, assume that it's approximately 0. Sorry, that was in kilograms. That's why I did that. Where's my eraser? Kilograms. That's why I wrote down that one. Okay, ignore air resistance and friction like I told you to do before. All right, so you can see it goes down the ramp and it will hit its maximum speed at B and it will come up, it will clear C for ignoring friction because C is lower than A. All right, determine the magnitude of the acceleration of the ball bearing as it passes through point C. How fast is the ball bearing traveling at point C? We're pretty much ignoring point B entirely. But point to note, let's have a look here. So, how high is point A? A ball bearing of mass 25 grams is rolled along a smooth track loop to loop. The ball bearing velocity maintains a track through point C, ignoring air resistance. Determine the magnitude of acceleration of ball bearings that passes point C. How do you work out the acceleration without knowing how high it was initially? I think that's a boo-boo. But we can do the first part anyway. Okay, to question 10, part A. The magnitude of the acceleration of the ball bearings that passes point C. No, we need the velocity of that, and to know the velocity, we need mgh. We're missing a key point of information here, because basically in the other questions you have I have to come back to that one. I think that's a mistake. Oh, I see. Actually, no. This is the key thing gives it away. So it just maintains. Sorry, I misinterpreted that. So there was enough information. This one is a tricky one, though. So it just maintains contact through point C. So it's just about to fall out. Actually, no. So just maintains contact means actually, sorry. Let's get this right. Okay, there we go. Force 0 at C. That's what I mean. Of course it can't. So neither of those can be true, sorry. All right. So, all right. So let's just take this out to C. So let's just kind of draw what we're talking about. Okay, what do they mean by that last sentence? I'm just wrap our heads around it. All right. So we give it a nudge so that when it gets to C, it's traveling. There's a minimum speed to be traveling such that you kind of drop, and it's not zero. You need to have a minimum speed so that you don't kind of fall out. Like if you're not traveling fast enough, you kind of fall in a parabolic arc. You'll still be moving kind of to the left, but you'll be falling out that way. All right. So ball bearings give enough speed so it's just going to make it around. Okay. Let's have a look. Think of the forces. All right. So you have your net force down that way. Now that's basically just going to be given by the weight force because Fn is approximately 0. So net force is equal to the weight force plus the normal force, which is 0 at C. And the net force is what's providing centrifugal acceleration, so mv squared on r. And just so happens that is actually the weight force that's going to do this. So they give us the math, but I don't think we actually need it. I think we can do this without it. So I think this is v squared equals rg. V squared equals 0.5 times 9.8. Sorry, just move this up. All right, so let's have a look at that. Okay, 4.9. Should know that. Okay, V equals, okay, 4.9. Getting in the way of things. Okay, get rid of that. Okay, 2.21 meters per second. So there you go. Was I working out what I needed to, or am I doing the second part? Okay, determine the magnitude of the acceleration of the ball as it passes point C. Well, I suppose I needed the velocity to do that. How fast is the ball bearing traveling at point? Is there an easier way to do that? Well, I suppose the magnitude of the acceleration is actually 9.8. So let's double check that. So what that actually means, mv squared on r. Okay. 0.025. Well, actually, no, it wouldn't be. Sorry, that's the force is the acceleration doesn't necessarily match up. All right, 2.21 squared on, lift it up, on 0.50. Okay. Okay, 2.21 times 2.21 times 0.025 divided by 0.5. Okay, and then that's the acceleration there. All right. How fast the ball bearing traveling at point C? I actually worked that one out first. Not sure if there's a different way to approach that question. But this makes sense. The way I interpret it, the other ways I was thinking of interpreting that question won't work out. There was enough information, and that I think this is the general interpretation of this question. All right. I think I'll just leave it there for now. This has been a long enough video already. All right.